In this video, we're going to work through an example to find the equation of the tangent line of an implicit equation. Let's jump in. So here's the problem. Go ahead and pause the video and see if you can find an equation of the tangent line to this equation at the point 3 comma square root of 7. Okay, so here's the answer. Depending on how strict your teacher is, they might accept this form, or if you wanted to fully simplify it down, this would be the most simplified version. But if you got this right and it was easy, feel free to skip the video. Otherwise, we'll dive into how we got this. Okay, let's jump in. At a high level, we're still finding the equation of the tangent line. It's just that a few details will be different because we're doing implicit differentiation rather than the normal explicit differentiation that you're used to. But all of the most important things about how to find the equation of a tangent line still apply. So think about it. The equation or the tangent line is still a linear equation. It's still a straight line, which means we're still going to be using point slope form. So y minus y0 equals m times x minus x0. We'll still be doing that. One detail is that in order to find y0 actually gets easier to find because they usually specify that point. In other words, we don't have to plug it into the function to find it, whereas we normally do when we're not dealing with implicit derivatives. So we already know quite a bit. We know that the function has to look something like y minus square root of 7, because that's the y value at the point in question, at the point of tangency. And then we'll also have x minus 3 here. So we know that the equation has to take on this form, but the question is really, what is m? How do we find m? There is where the implicit differentiation comes in rather than the normal derivative. But again, we still take the derivative of our equation and plug in this point to find the slope at that point. So the derivative still means the same thing. It's just we need to find it with implicit differentiation instead. So how do we do that? Remember, we're dealing with x squared plus y squared equals 16. That's our equation. And in order to take the derivative, we need to implicitly differentiate both sides. So we'll take the derivative with respect to x of the left, and we'll take the derivative with respect to x of the right. The derivative of a constant on the right is 0. The derivative of 2x with respect to x is 2x. And again, I won't explain exactly the rules for implicit differentiation. We're covering that in another video. I'm just going to kind of work through it here. So the derivative of y is going to be 2y times dy dx. And then effectively, we want to solve for dy dx. If we subtract both sides by 2x, so we can get 2y times dy dx equals negative 2x. And then what we can do after that is we can basically divide by 2y, so on both sides. So we will get 2 dy dx equals negative 2x over 2y. And then we can simplify that. So final answer, for the derivative at least, is negative x over y. There you go. That's the derivative. This equation will tell us the derivative at any point on the curve. Now, what point are we actually dealing with here? 3 comma square root of 7. Therefore, at this specific point, hopefully it makes sense that the slope will be negative 3 over square root of 7. Just using this, plugging in this x coordinate and this y coordinate to the derivative equation, basically, to find our slope at that point. So there we go. That's how we get this. Yeah, I'll just rewrite this real quick. So this is the equation in point slope form of the tangent line to the curve at this point. Now, depending on your teacher, they might be a little bit stricter about this. So they might want you to do a couple of things. First off, this is in point slope form. Usually they'll let you leave it in this form, but if you have a very strict teacher, maybe they won't. So one thing you could do is you could basically transfer it to slope intercept form. That's generally the most simplified version. So you have negative 3 over square root of 7 times x minus 3 times negative 3 over 7. That'll actually be positive 9 over square root of 7. And then you could basically add square root of 7 to both sides. So you can get y equals negative 3 over square root of 7 times x, that's the slope, and plus 9 over square root of 7 plus just square root of 7. Now this in and of itself is still a little bit ugly. So you might, if you're already trying to put it in the simplest form, maybe you want to do some more work as well. One thing you can do is deal with these kind of ugly denominators here by rationalizing the denominator. So for example, if you want to rationalize these, you can basically multiply by square root of 7 divided by square root of 7. And then you can do that here as well. Square root of 7 divided by square root of 7 to rationalize the denominator. Now think about this. In the numerator, we'll have negative 3 times square root of 7. But what is square root of 7 times square root of 7? Well, you can think about it as negative square root of 7 squared, because we have two of them multiplied together. But then you can think about it as if the square and the square root are canceling out. So long story short, you're just going to end up with 7 in the denominator. And that's kind of the whole point of rationalizing the denominator. Where it's currently irrational, we're making it rational. That's what we mean by rationalizing the denominator. You can go through a similar process over here to get 9 radicals, or I'm actually going to write it a little bit differently, but 9/7 times radical 7. Just like you could think of this as negative 3/7 times radical 7. You'll see why I'm writing it in this form in a second. It's because I want to basically combine these two numbers. And again, this only shows up because we're dealing with irrational numbers. Like normally, these steps that we're doing now would not show up in a typical problem, I'll say. But if you're dealing with this exact problem, then they do. So how can we simplify this? Well, you can look at this as radical 7 times 1. Remember, multiplying by 1 doesn't change anything. But in order to get a common denominator here, you can make this 7 over 7. So if you multiply by 7/7, well, that's just 1. That doesn't change anything. And then we can get kind of a common denominator here that we can actually use. So 9 plus 7, hopefully it's clear that would be 16 over 7 times radical 7. And if that's not clear, just imagine what you would get if you factor out radical 7. It would just be 9/7 plus 7/7, which is 16/7. And then you could multiply by radical 7 afterwards. And then we still have this portion right here, negative 3 over 7 radical 7 x. So there you go. This is, I think, the most simplified version of the equation. Although, just to reiterate, if I was a teacher, I would not mark you wrong for this. I would consider this correct, but maybe your teacher would mark it wrong. So there you go. Hopefully that makes sense. Now let's take a look at this on Desmos. So looking at this on Desmos, we can see that, yeah, it actually does look like this is the equation of the tangent line to the implicit curve, which actually happens to be a circle in this case, if you recognize it from the form. But even though it's a circle, and even though it's not a function, it fails the vertical line test, which is why we need to use implicit differentiation to begin with. The derivative still is the slope of the tangent line at a certain point. So that's still true. And again, if I turn on this one, the simplified version, you can see it's the same line that we're talking about. So yeah, this really is the equation of the tangent line to the curve, even though it's implicit. So there you go. That's how you find the equation of the tangent line for an implicit equation using implicit differentiation. Hope that makes sense, and I will catch you next time.